Bismillahirrahmanirrahim. In this lecture, I will discuss about the third colligative property, which is the freezing point depression of the solutions, or you can say lowering of the freezing point of the solution as compared to the pure solvent. And colligative properties are the properties that depend on the amount of the dissolved solute, but not on its chemical identity. And in the first lectures about the colligative property, I have discussed in detail about the colligative properties. And the previously we have also discussed about the lowering in vapor pressure and the elevation of boiling point of the solution as compared to the pure solvent. Now, coming to the freezing point depression, and these are our main objectives, learning objective. The first one is I will explain with the thermodynamics parameters why the freezing point of solution is lower as compared to the pure solvent, and what are the benefits of this freezing point depression, particularly with the determination of the molecular mass of the solute. And I will explain the derivation or the equation to be used for the determination of molecular mass of the solute. And you can use the equation to calculate the freezing point depression and the molality of the solution. So this is the general graph about the vapor pressure versus the temperature. And if you increase the temperature, first there is the freezing point of the solution, and then the solvent, and then the boiling point of the solvent, and then the boiling point of the solution. So solution is having more boiling point as compared to the pure solvent. That's why this is delta T. P is the boiling point elevation, and this is more for the solution as compared to the pure solvent. And the freezing point of the solution is less opposite to this one as compared to the pure solvent. That's why this is called the freezing point depression. And this is represented by the delta T. F is the freezing point. Delta T is just the difference in temperature. And here the difference is the freezing point difference, or the freezing temperature between the solvent and the solution. So in the next slide, I will explain in detail what about this graph. So coming to the main learning point in this colligative property, which is the freezing point depression, or the freezing point of the solution is lower as compared to the pure solvent. And I will explain over here with the three thermodynamics parameter. One is the change in free energy, change in enthalpy, and change in the entropy. And this is called the actually enthalpy, or the free energy of fusion, free energy of change in enthalpy of fusion, change in entropy of fusion. Why this is? Because here your liquid is converted into the solid, and this is the change in state from liquid to the solid, because here we are considering the freezing point of the solution and the solvent. So first let's discuss the what would be the effect on the change in entropy. So these are the three main components are given over here. One is the solid. Solid mean when it is the solvent is freezed or the solution is freezed, that means it is converted into the solid, and solid and the solution. So what would be the difference in entropy? The solid is having least entropy as compared to the liquid. That's why it is placed at the bottom. And then when the solid is converted into liquid, it may be a solvent, and the solvent is having less entropy as compared to the solution, because there is less randomness when you prepare a solution or dissolve a solute into the solvent, then the randomness increases. That's why the solution is having more randomness as compared to the solvent. So now, what would be the change in entropy or entropy of fusion for the solvent? This is the solvent from solid to liquid. Actually, here we are discussing the freezing point. You may think about the reverse form: solid solvent is freezed into the ice or the solid, or solution is freezed into the ice or the solid. So there is no actually the difference in explanation. So this is the difference between the solid and the solvent. The change in entropy is given over here, and this is the change in entropy of fusion for the solvent, and this is the change in entropy of fusion for the solution. And now what is the conclusion? The change in entropy for the solvent is less as compared to the change in entropy of the solution. And this is clearly visible over here, because solvent is having less entropy, so the difference is less. Solution is having more entropy, so the difference as compared to the pure solid is more. So this is uh, the effect of the change in entropy. I will use this one to further explain the freezing point or the freezing point depression. Now, consider the second thermodynamic parameter, which is the change in free energy. And because the liquid and the solid phases are in equilibrium at the freezing point, so when these both are at equilibrium, then the change in free energy will be zero. So change in free energy is zero at the equilibrium. Now, what would be the next equation? This will be delta H will be equal to T delta S. And if you want to get the TF is the freezing temperature. That would be delta H over delta S. So now I'm going to conclude with the change in entropy. Actually, why the freezing point of solution is lower than the pure solvent. So now consider again, if this is similar for the solvent and the solution, the change in enthalpy is same for the both solvent and the solution, then what would happen? And this change in entropy is larger for the solution as given over here, and I have explained before. This is larger for the solution, and if this is large, this would be the less, and this is the freezing point, and this is smaller for the solution, and now this is called the freezing point depression, or the lowering of the freezing point of the solution as compared to the pure solvent. So this is the reason, thermodynamic reason, why the change freezing point is lower, or the freezing point is depressed when solute is added into the solvent. That means when it will form a solution, then the solution is having small freezing point, or the smaller freezing point as compared to the pure solvent, and this is called the freezing point depression. Now coming to the derivation, this is the same way I will explain as I have already explained in the boiling point elevation, because this is the same way to derive the equation. Now consider the this way of the graph, and this is the point A, point A is this is the pure solvent. And this is let's suppose this is the point A when the solvent freezes, and this is the freezing point of the pure solvent. It is represented at TF naught. And this is the vapor pressure of the pure solvent. This is called the P naught. So this is the point A. Along the y-axis, you have plotted over here the pressure. This is the vapor pressure of the pure solvent, and this is the freezing point of the pure solvent. So at the same temperature, this is the point B, and this point is for the solution. And now this solution is having vapor pressure of this, and you can easily understand over here P1 is less than as compared to the pure solvent. And this I am repeating again and again. And in the first lecture, this is the lowering of the vapor pressure in case of the solution as compared to the pure solvent. So solution is having less vapor pressure as compared to the pure solvent. So this is point A. This is the vapor pressure of pure solvent, and this is the freezing point of the pure solvent. And this is the point B is the vapor pressure of the solution. So if you want to freeze the solution, you have to move towards this point C, and at this point, if you extrapolate on the x-axis, this is called the freezing point of the solution, and this is represented by the TFS, freezing temperature of the solution. So you can see over here, this is having value less as compared to this, and this is called the depression in the freezing point. And this difference between pure and the solution, that is represented by the delta TF, and this is the change in temperature, and particularly this is the depression in the freezing point. So I will be using 3 points A, B, and C to calculate, to drive the equation. This is the final equation. I will reach to this form. So I will be using just a slope of these line. Slope mean what are the values at the y-axis. This is the A to B. A is the P naught, B is the P1, this is the dy, and what is the dx? It is the CB, and C is the TFS, and B is the TF naught. TFS is the freezing temperature of the solution. TF naught is the freezing temperature of the solvent. So this is the same derivation. K is the slope, dy over dx. As I have explained, dy is the AB, dx is the CB, and AB is the P naught minus P1. The difference at the y-axis, this is the P naught minus P1. For x-axis, TF naught minus TFS, TF naught minus TFS. Sorry, this is the mistakenly written higher temperature minus the lower temperature. So you can just replace over here TF naught minus TFS, higher minus lower. Higher, this is higher, this is the lower, depression in the freezing point, and delta P divided by delta TF. Delta P is the difference in the vapor pressure of the pure solvent and the solution, and delta TF is the depression or the change in the temperature of the freezing point between the pure solvent and the solution. So according to the Raoult's law, we have discussed before, this P naught minus P1 or delta P is the lowering of the vapor pressure, and this is equal to P naught x2. And this is the same is given over here, P naught minus P1, this, which is the delta P, which is equal to P naught minus x2 according to the Raoult's law. P naught is the vapor pressure of the pure solvent. X2 is the mole fraction of the solute. 2 is representing the solute. More will be the solute, more will be the lowering in the vapor pressure, and this is the Raoult's law. So putting the value over here, this is the K from K is equal to delta P over delta TF, and delta P is equal to P naught X2, and this is the same. And now if you want to get the value of the delta TF, the change in freezing temperature or the depression in the freezing point, that would be equal to, just K will divide over here, and this equation will become this. P naught over K, both are the constant. This is the vapor pressure of the pure solvent with the constant. K is the slope, and these two are the constant. And let's suppose these are the proportionality constant, and this is equal to another constant that is called the Ke. Just to make this equation as the simple equation. So delta TF will be equal to Ke x2. I am replacing the P naught over K with the Ke, and this equation will become this. Now I am opening this equation. Actually, I'm elaborating the mole fractions. And why I'm going to do that? Because I want to calculate the molality and the molecular mass of the solute. So this is coming from the mole fraction of the solute. And as explained before, X2 is the mole fraction of the solute. And what is the mole fraction of the solute? This is the moles of the solute divided by the total moles. So total moles mean moles of the solute plus moles of the solvent. So this is the mole fraction. That means X2 will be equal to N2 divided by N1 plus N2. Now, the moles of the solute are much less as compared to the solvent in a solution. So you can neglect the N2 in the denominator. So this equation will become this N2 divided by N1. Now you already know that what are the number of moles? These are the given mass divided by the molecular mass. So this is N2, N2 are the moles of solute. So this is the given mass of the solute divided by the molecular mass of the solute. Given mass of the solvent divided by the molecular mass of the solvent. And when you rearrange this equation, this is finally become this equation, just a rearrangement of this equation. So again, this is coming from the previous slide. Now look at the this point. Ke is the constant and M1 is the molar mass or the molecular mass of the solvent, and these two remains the constant, and these two are equal to the Kf, which is the constant, and it is the property of the solvent. That means it will vary from solvent to solvent. If it is the water, it will be different, and if it is another solvent, let's say ethanol or the methanol, these value will change because this is a property of the solvent. And here Kf is called the molar freezing point depression constant, or simply you can say this is the cryoscopic constant. Now replacing the KEM1 with the Kf, sorry, this is again mistakenly written over here. This is the Kf because the derivation is the same. So this is just the misprint over here. So this Kf, and this is rightly written over here. You can use this equation to calculate the molecular mass of the solute. This is M2. So if you know what is the weight of the solute is added into solvent, and you know what is the weight of the solvent, you can easily calculate the molecular mass of the solute with the known value of the depression in the freezing point and the constant, which is the cryoscopic constant. Now you can convert this equation in terms of the molality. And if you want to calculate the molality, you can further modify this equation. And molality is simply the number of moles of the solute per kilogram of the solvent. So actually this term is the molality, and how it is the molality. Molality mean, as I have explained over here. So W2M2 given mass of the solute divided by the molecular mass of the solute. These are the moles of the solute. So to convert into the mass of the solvent to the kilogram, you have to divide by 1000. So W1 over 1000 is the kilogram of the solvent. So moles of the solute per kilogram of the solvent, actually this is the molality. So you can replace this whole term with the small m, which is the molality, and this is the final equation. You can use this equation to calculate the molality just by knowing the cryoscopic constant and the depression in the freezing point. You can get the value of the molality. And finally, what are the units of this constant? Cryoscopic constant. You can easily calculate this one. Kf will be equal to delta Tf over m, and the unit for this is just the temperature, and the temperature is having unit Kelvin or the centigrade, and the molality is the moles per kilogram. So this is under delta TB, or temperature over molality. So the units will become reverse. So final units are the K kilogram per mole or centigrade kilogram per mole. So this is all about the third colligative property, which is the depression and freezing point. In the next lecture, I will explain about the fourth one, colligative property, which is the osmosis and the osmotic pressure. Thank you for watching.